yes, is at some point I actually heard you referred to as Mr. Dust. Self-proclaimed, probably not. I started to think about it. I first met Karl, I think it was 1999 at a conference where I was starting to work on star formation in galaxies, and I left utterly depressed after talking to Karl about how much we don't know about dust. I got over that. And nevertheless, then we were both, well, I joined as a postdoc to the MIPS team where you're already well established there. MIPS was the mid-infrared and far-infrared instrument on Spitzer, where then Karl and I both worked savagely on various data coming off there. Again, trying to understand dust. Turns out we still don't understand dust. He's now a staff astronomer at the Hubble Space Telescope Science Institute, trying to understand dust, combining various surveys on, I think it's the Magellanic Clouds, right? Is this one?
We're also talking about M31.
Here. Well, also
this is
M31.
This is the Magellanic
So,
Clouds.
so it's the large things that you can resolve with telescopes, even as small as Spitzer, Herschel, to understand how they radiate in their mid and far infrared. I'm going to try to turn out the lights, but let's go ahead. Thank you. Karl. Welcome, Karl. And
Thanks,
take it away,
everyone.
Karl.
Lots of dust. That's the goal. Here's my outline. I'm going to talk a bit about why I care about dust. The evolution of dust in the ISM is the thing I'm interested in these days, both from the infrared submillimeter, well, I'll talk about how it's a sensitive probe of the total column of dust, as well as emissivity variations. No, I can stand pretty close without eclipsing. All right. And then in the ultraviolet, optical, and near infrared, which is in progress, this is Hubble data to probe, again, the column of dust, but also grain size and grain composition. And that one's got the best acronym, that's the BEAST, which you'll see more of. Best acronym. And then trying to combine the two is we've started on, but it's more future work. We want to combine the two to actually understand more of the environmental variations of the dust emissivity, and we can couple that with the environmental variations of the dust grain size and so on. I mean, the main conclusion is easy, and it's not very quantitative, is that we see lots of dust property variations are seen in galaxies, and really they correlate with environment. And one of the things, the direction I'm going more in my research is going more into the theory and modeling to understand what that tells us about the fundamentals of dust grains. Comments, questions, discussion, random thoughts during the talks are encouraged, including heckling. Although for heckling, I promise to heckle back. That's your only, and I've heard all the dust jokes. So you're going to have to try to be original if you're going to heckle. Okay, so I of course have collaborators. I don't work in a vacuum. I have many collaborators. But for this particular work I'll talk about, there's in the Magellan Clouds, it's mainly the Heritage Herschel legacy, which is mapping both clouds with Herschel, Pax, and Spire, but also the Spitzer Sage surveys. And really it's Julia Roman Duval and Margaret Meixner, Carolyn Bott, and now Jeremy, and I can't spell his first name, who's a PhD student that Carolyn and I shared. And then in M31, which is the UV optical and near infrared, it's really the FAT, also a great acronym. M31 multi-cycle legacy. And there's a bunch more people on that. That's a big team and lots of people have contributed. And I'll show authors to papers to give you the full list of collaborators.
It's amazing that acronyms just randomly spell words that are...
Yeah, randomly. The BEAST works. It actually doesn't random at all. It's the best acronym. That's what makes it great. It's a great acronym and it's correct. We'll get to it. Sorry, I'm a little proud of that one. So why? There's my answer. Why would I do this? Is because it's dust. It's fun. Okay, maybe that doesn't do it for everyone. It really does do it for me. It's kind of neat. Why? So dust affects observations. This is the pesky dust. Lots of people don't like dust because it gets in the way of what they're interested in studying: star formation, gas physics, etc. This is a very good one because it keeps me funded. Right? Everybody wants it dealt with. They don't want to do it. They think it's my job. And I try to convince them I'll do that, really, at some point. But more interestingly, from the physics standpoint, dust surfaces allow for where we get our molecular hydrogen. Okay, that's where the efficient molecular hydrogen formation is. We need molecular hydrogen to do star formation. Dust also shields, so that star formation, we wouldn't have nearly as many stars now as without dust because it provides the shielding and allows the gas to cool, so we can actually condense. Dust is composed of metals, so if you're interested in the metal life cycle in a galaxy, you better think about dust, because that's what dust is. It's composed of metals and has a significant fraction of the metals in the ISM are in dust. A little more different, dust has a lot of physics. This is what has kept me interested in dust physics, in studying dust for a long time, is there's a lot of the physics that I learned in grad school that I can apply to my studies. Everything from classical solids to solid state physics, quantum physics. And very small grains, thermo, radiative transfer, all that good physics is actually in dust grains and their effects on observations. And I also love physics. Physics is fun, so that kept it for me. Interestingly, and this is something that's kind of come out of Spitzer and Herschel, is dust actually traces all phases of the ISM, unlike most gas tracers, which trace one or only one, well, usually only one phase, right? And so there's an interesting thing here with dust that you can actually trace the total ISM in a galaxy with one set of observations instead of needing multiple. Now, it's not that simple, right? Things are not necessarily linear, but there is some very interesting thing there. Dust varied, dust variations with environment do encode the past processing and the past, what has happened in that galaxy. And this is what's interesting me these days. I'm very interested in how dust variations and what they mean about what has happened in that galaxy. Maybe what has really happened to the dust, and that's a side product. We can learn something about shocks, radiation environment, etc. So where do we get dust from? Nominally, we usually think about it, dust condenses in the winds of stars, asymptotic giant branch stars, red supergiant branch stars, supernova. These are kind of the three places where we think dust comes from. Then how do we get rid of dust? Dust is destroyed, it's also consumed in star formation, but the majority of it we think is destroyed in supernova shocks. In fact, so much so that we shouldn't have any dust. Supernova shocks are so efficient at destroying dust, there should be no dust left in the Milky Way. So that's a bit of a, this is the whole dust life cycle. Also something that's really gained a lot of steam, especially with the Spitzer-Sage surveys, where we're able to actually measure everything at once in the galaxy. So the conclusion to this, and this is not a conclusion, this has been around since Spitzer, Bruce Drain worked on this many years ago, etc., is that dust condenses in the ISM itself. Theory says not fast enough, but if we can't come up with any other way to do it, we need to do it in the ISM. So that gets me thinking, well, what about observations? I do a lot of observations. I also do a little theory and modeling, but observations are probably my main thing. That may have implications, if you think about that, on what happens at higher redshift. I know there's some people who worry about things at higher than local group, which is where I am these days. But if you can condense dust in the ISM itself, that means you might be able, should be able to get dust very, very soon in the universe. And this jives, we see dust at very high redshifts, and that was a bit of a surprise from a dust theory point, because we thought it all came from AGB stars and they're a gigayear. Right? So that would put a limit on how redshift you can see dust. You have to see it at higher redshifts than that. Okay. Nearby galaxies. I like nearby galaxies. In fact, the more I do this, the more nearby I like them. Except the Milky Way. The Milky Way is too close. They provide excellent laboratories to study dust evolution, and the local group is really the ideal place from my standpoint, given our current observational capabilities. So that means we can resolve individual stars. A lot of the complications of not resolving individual stars, the rate of transfer complications, go away if you could just say, this is a star. I'm going to measure along that line of sight. Observations exist over a very wide wavelength range, and a lot of this has happened in my career, which has been interesting to see. I started off doing much more theory, doing much more radiative transfer, dust radiative transfer. Realized that I needed better observations, especially in the UV and the infrared, because this is where the UV is where the energy that powers the dust emission comes from, and the infrared is where it comes out, and so that's how I got into more observations. But now we have all these observations, and it's quite extensive. And we're getting more and more as time goes on. So, well, Milky Way, you can do all this too, but the problem is we're inside it. It's a little more complicated, and you have to look through part of it to see the other part of it. An external galaxy, you get to see the whole galaxy, and all the parts of the galaxy you get to see on the same basis, right? Especially things face on are really nice, because there's less confusion along the line of sight. All right, so how can you probe dust ISM evolution? That's what I'm interested in. Variations in the dust, so dust extinction curves, we can measure them spectroscopically and photometrically. Dust IR emissivity variations, that's IR photometry, plus we need the stars. We need to be able to have some measurement of how much dust is there that's independent of the IR. Right now, when we measure the dust mass from an infrared SED, we assume a constant emissivity, right? We assume it's the same emissivity everywhere in the galaxy. We know that not to be correct. But we assume it, but how do we then calibrate it? How are we going to actually figure out why that emissivity variations? And what I mean by emissivity is the IR emission given a unit of dust mass, right? And so say you make a fluffier grain, it actually has much more efficient at emitting IR emission than a solid grain. for the same mass. Okay, so that's going to, we're trying to figure out what the mass is from the IR mission. It's going to depend on what we assume about what the dust grains are. I'm getting into ice variations. This is future, right? So ice is something you can measure in absorption in 3 microns and beyond. And this is really something where I think JWST in particular is going to make a really phase shift in our understanding of the ISM. Right now, in the Milky Way, we have maybe 150 sight lines for which we have ice measurements for background stars. And a couple of observations with near spec with the multi-slit assembly will well past that. We could do it in a nearby galaxy like that. And you bypass all the work that has been done over many years on ice in our galaxy. So now we can take ice and just not just do it in our galaxy, but other galaxies. Very interesting, because ice is one of the things we know is that's molecular material. We know we're really in a star-forming cloud. Also, gas-to-dust ratio is probably one of the best ways of looking for dust formation in the ISM. All these other probes just tell you things about that the dust properties have changed. They've gotten bigger, they've gotten smaller. Maybe I've done it by coagulation. But if I really want to know, has material from the gas phase moved into the solid phase, it's probably gas-to-dust ratio is the only probe I can think of that's actually clean, in the sense that the gas in this ratio is completely dominated by hydrogen. Not much hydrogen goes into the dust. And so that part of the ratio doesn't change. But the dust is going to be changed by removing or adding the atoms, and mostly metals, in and out of that phase, either by destruction or accretion. And so if you see gas-to-dust ratio variations and you're certain you're actually measuring true gas-to-dust ratio by mass, that's telling you you're changing. You're actually moving things between the 2 phases of the ISM. That's why I think that's the most interesting in the direction I'm going. I'm going to talk about these 2 today. So let's talk about the infrared submillimeter. This is not a new thing to do. The far infrared submillimeter measures the total grain volume. It doesn't really care what you assume about the grain radius. It's really just about the total grain volume you've got in that region you're measuring. And this is back a little before my time. And already this was a review article, and it already had values for beta. Notice, interestingly enough, beta is not a constant over the wavelength range. And this is something that maybe we've rediscovered. Laboratory work very clearly shows that beta is not a constant. And there's various interesting breaks in the emissivity law for dust grains like amorphous carbon, amorphous silicates. So just from Spitzer, this is work by the SINGS team. Lots of nearby galaxies measured, fit them with a reasonable dust grain model. This is Bruce Drain's model that he works on for a long time. He's worked on it, continues to work on it. Gets pretty good math, and the question is, how do you know you've got about the right dust mass? Well, one way you can do it is you can look at the gas to dust. In this case, it's Bruce. He's Mr. Dust. I can't be Mr. Dust. When Bruce is still around, I'm out. I can't do it. He does dust to gas ratio. Of course, the dust is the important thing. And you see now, you can say, all right, what is it, and how does it vary with metallicity? So that's oxygen metallicity. Dust is metals. So if you have fewer metals, you have less dust by definition, right? And so you can actually see this is just the relationship due to metallicity as you drop. Does the gas-to-dust ratio, the dust-to-gas ratio go down with metallicity? And it looks pretty good. Ignore these guys here and just look at the nice green ones. It's a reasonable correlation. So the dust masses we're getting out are reasonable. Although we'll come back to that in a moment. Well, but then one of the things that Herschel really brought up is something that had been known from the ground, and there's something called the submillimeter excess. And so this is a very observationally kind of defined thing where if you take observations below 200 microns and you fit models to them, either simplified modified black bodies or maybe even more complex models, and you extrapolate the longer wavelengths, you see the submillimeter, in the submillimeter, 450, 850, etc. There's more emission than you expected from your extrapolation. Well, you used the word extrapolation, so obviously you were doing it wrong. But even then, even when you tried to fit it, you couldn't fit both the far infrared and the submillimeter with the same model. Let's say it had a simple modified black body with a beta law. Well, all right, but it's ground-based. You're using ground-based data to do submillimeter. It's hard. With Herschel, we now were able to really explore this in detail, right? And Herschel had these great observations from space in the submillimeter where you didn't have to worry about the atmosphere as much at all. and you can really explore it. And the really odd thing, I think, that there were two possible explanations. Either you have emissivity variations, which hint that's the answer, but it could also have been colder dust, where we have, less than 10 Kelvin dust. But then the problem is, in order to get less than 10 Kelvin dust to emit that much, that's a lot of mass. That would completely dominate the mass of the dust. So this is something that went back and forth. And without Herschel, we wouldn't have had enough data to, I think, really show this. And so I'll show this, how we did this. It's also a grain property. So if it really is emissivity variations, which it is, then it tells us how the grains are changing, right? So amorphous silicate, amorphous carbon, and amorphous silicate, carbon, amorphous silicate, there we go, have different beta laws measured in the lab. So if you see the beta law varying in your observations, you might be changing the ratio of these two grain components. So that can tell you something about the grain composition. So there's Heritage, one of these key projects out of Herschel. Let's get together 100 of our friends and propose to, oh yes, we got a question. First
yeah, very basic question.
Yes.
I think. So why does dust not just follow a simple black body? Why do we need a modified black body?
Because right. It's not a black body, right? Nothing's a black body, perfect black body. So it actually has an emissivity, right? So it's got some properties that tell it. For example.
Okay, so beta tells us something about the emissivity.
Yes. Oh, so I'll define what beta is. Sorry, it's just usually take the black body, multiply it by lambda to the minus beta, and that's lambda to the minus beta is a good approximation of the laboratory observations of what the actual emissivity or absorption is, right? We assume the absorption and emissivity are the same.
Is a black body beta minus 2? Or is that not true?
No.
There's always a
No. A black body is no lambda to the minus beta at all. Just a black body is straight up. Lambda to the minus 2 is kind of the standard one we all use. That's all. It's also a limit on a simple harmonic oscillator, which is the
Interesting.
Yes, which is not true for. I can't remember. I've got it in my backup slides which one it is. One, can't remember if it's carbon is -1 and silicates are -2.
There's a two molecular structure.
Yep. Yep. I'm good?
Sure.
All right, just checking. Magellan Clouds, big project, you get lots of data. The nice thing about the Magellan Clouds, and we're lucky to have them near us, I would say, is that one, we can resolve them very, very well. We can get good observations, even at effectively 1 arc-minute resolution is still 10 parsecs, which for extragalactic observations is spectacular. For galactic observations, not so good, but hey. The other nice thing is they have metallicities of between 1/2 and the LMC is 1/2 solar, and the SMC is 1/5 solar. That's a very interesting set of metallicities. One, you at least have 2 more points other than the Milky Way. There's also lots of indication there's something interesting happening in the ISM between 1/2 and 1/5. Likely some kind of phase transition is going on. I'm not going to talk more about that, but it's a nice coincidence that we've got that. Here are the 2 papers, one I led and one Giulio Roman-Duval led, on the talk about dust mass. And so you can see there's even more collaborators than I can put on there. Lots of people. So there's the data. It's a standard set of Herschel data, packs 100 to 500. Subtracted out Milky Way diffuse cirrus emission. You have to worry about that if you're doing big, giant galaxies. Subtract the background, convolve them all to the lowest resolution. When you've never had 500 micron or 40 arc-second resolution before, convolving everything to that and working at that means, okay, yes, you threw out the nice resolution of the shorter wavelengths, but you've never had it before, and now you have multi-wavelength data that have the same resolution. You don't have to worry about resolution effects. We've always said later we can go back and use the higher resolution we never. Who knows? They've also been rebinned to 56 arc-second pixels to make sure I have an independent measurement, right? The full width at half max is a little smaller than that. So I really wanted to try to have only one independent measurement.
And the higher resolution data would give you indications, for example, if you had more emerging into star forming regions, for example. So if there was higher variance, for example, dust properties, you might be able to see if
Yeah,
that was.
we could do that. It can be done.
Yeah, right.
That's not the problem. It takes a lot of work to get this stuff out. And so
Yeah.
someone's got to be motivated and pushing on it. It could be you or one of you, or the data's all there. There's the data. I can even show it to you. It looks pretty good. There's the H1 data. We also added in. We use that a little later. Gives you an idea of what the galaxies look like. They don't change a whole lot in morphology over this wavelength range. That's the SMC. Also, but look how beautiful that data is. I spent a lot of time working on the data. You got to show it off. All right. So now I'm going to do some very simple things. I'm not going to do something as fancy as Bruce Strain's model, although Jeremy has done that now. We're just going to use simple dust emission models. Simple is always good. I've been taught that from my PhD advisor. Try the simplest thing first before you go complex. And so I'm going to use three simple models. They're here, and I'll explain them in just a second. There's the equations. You can read the paper. So this is probably the most commonly used one, which is just a simple emissivity law. There's the equations. Basically, you have this is the emissivity. This is the emissivity law. And you multiply it by your black body. Right, that was back here, K lambda. So that's what your surface brightness is, this emissivity law times the surface density of dust times the black body. This is very simple. This is how dust grains emit. This is how all even complex dust grain models model the dust emission. All right? They just then sum over many grain sizes and grain compositions to get that. But this is at the basis what it is. This is the standard one that pretty much gets used almost all the time, and this is just to show you what happens as I change the temperature. Now, of course, it shifts to longer wavelengths, but it also, this is for the same mass of dust, it also gets fainter. It's a black body. The total drops as you go to cooler dust. If you change beta, right, there's how beta changes things for the same mass of dust, same temperature. Gives you an idea. There might be some degeneracies there. So now the other two ones, and this is where we already had an idea that this model wouldn't fit all our data based on previous things. We'd have need some break or some extra component. And so there were two other models. This is kind of choosing between the two possibilities. So we have a broken emissivity model, which basically says I have one power law up to some wavelength, and then I break it. And I either do this, that, right? That's all. As simple as possible. The other one is I'm just going to have two components. They'll have, let's see if I give them the same emissivity. I can't remember anymore. Yes, they'll have the same emissivity law, but one will have a cooler temperature than the other. Simple. Simple is good. The older I get, the simpler I like things. It's a little scary. I think my advisor is laughing at me now. So this also was where I started getting into probabilistic fitting or Bayesian techniques, etc. That can either be a positive in your mind or a negative in your mind. It depends on what you feel about fancy statistics. It's not that fancy, and that's what worked for me. The nice thing about this is we can really allow the full range of parameters to be explored. I actually do this on a grid. We don't do any ensemble sampling. We just do it brute force. Brute forces can be very fast, depending on how you code it. The thing that really sold me on going this route was I could now get uncertainties on my fit parameters. Okay, so that means I can now take my n-dimensional likelihood function and marginalize it or integrate it over the other parameters and get a 1D that says, here's what my dust surface density is, and here's the width of the sucker. Right? And that, to me, was the convincing thing. I've always wanted to get reasonable errors. I've tried lots of other ways, F-tests, bootstrap. It was never very satisfying. For me, this worked, very satisfying. You can also do the more complicated things and look at correlations. I would say that the nice thing about Bayesian thing, and it has taken me years to get to this realization, it's not straightforward, it really encouraged me to be more quantitative about my assumptions. Those are called priors, but that's what it really did for me. The other thing we knew a lot about, I know too much about calibration, and that we know that the calibration of things like Herschel and Spitzer are highly correlated. And not on the order of 1%, but on the order of 10%. And if you think about what that means, if your error bars are random and you're trying to fit a temperature, then you have this variation is allowed, and so your temperature can vary a lot. But if they're not random and all you can do is move the shape up and down, your temperature can't vary by much, right? So now you went from something that might be a T to the 4th to the mass of dust to something that is just single T to, just a scaling factor. And so it means that before you allowed a much larger range of temperatures, you now want a much narrower range of temperatures, which means your dust mass has now gotten much better constrained.
So it's going to be correlations measured with different band passes.
Yes, exactly.
Right, so both doing.
If they both go up and down, that means the shape doesn't vary as much. Okay? And so the nice thing about this, and again, this is one of these things where I didn't know what to ask people. How do you put a covariance matrix into a chi-square? It turns out you need to know the words multivariate Gaussian. I didn't know them at the time. I had a hard time getting people to tell me, but it's actually fairly straightforward. Your standard equation just breaks down into this is just your difference observations minus model, and there's an inverse of a covariance matrix multiplication. You get a chi-squared out. It's pretty easy if you know what to ask for. And in the case where you don't have any covariance, that reduces to your standard equation. So this is nice now. Now I know how to put covariance in. And it really does matter. Here's the absolute flux calibration covariance matrix for, this is Pax up in this corner, and this is Spire. Turns out they use stars, they use asteroids, so they're not covariant with each other, but they're highly covariant inside, right? So this is 8%, and all 3 bands of Spire are completely correlated at the 8% level. There's also repeatability, i.e. you come back to the same source, you get the same answer. Those numbers are much, much smaller, but these dominate. And if you don't put them in, what you get. And then, because I'm doing surface brightness measurements, I have a background I subtracted off. Well, there might be covariance in the background. The nice thing about this is I can just calculate it. It's easily measured. You have a whole bunch of points, and you can ask, are my points in this band on average higher in the same direction offset in another band? And that's the equation, straightforward to do. And if you just make the measurement, here's the covariance matrix for the SMC background subtraction I did. It's in Megajansky squared, but if I put it into a correlation matrix instead of a covariance matrix, you can see that the background is highly correlated, especially in the Spire bands, and even in the Pax bands. Okay?
It's mostly to the cirrus residuals, or
It's cirrus residuals, the background galaxies, right? If there's a galaxy
Okay.
in one band, it's going to be there in the other band, and so it's going to be
any structure
Yeah.
that would
In-
affect your background.
In general, if you see, these could have been negative. There could have been negative terms, right? That would mean they have an antiquote. They're not. In general, a positive probably means it's a physical,
Structure.
it's something in the
Yeah.
sky you see. I did this for the whole Spitzer and Herschel bands, and there are some weird negative correlations, which probably tells us that there's some instrumental artifacts left. But that's just to, fun with your data. I don't know what to do with that. Okay, so here's the model grid thing. We did it on a grid. We did it over what we think is a wide enough range to cover everything. And if it wasn't, we just made it bigger. The nice thing about doing it on a grid instead of using an ensemble sampler is you're not going to get stuck in a minute. As long as your grid is fine enough to resolve the PDFs, this is, I would argue, is more robust than a sampler. Even though it's not as cool as using, say, MC. But, hey. The other thing we did, which was actually, I didn't care about this. I didn't really care what the total mass I got out of the Magellan Clouds. But it turned out this is one of the nice things about being on a team. On the Heritage team, they really care. Because one of the goals of the SAGE and Heritage projects was to do the dust life cycle in the Magellanic Clouds, i.e. we're going to measure all the AGB stars, all the RGB stars, and we're going to add up, and we can, from those Spitzer and Herschel observations, we can say how much dust is coming out of each of those stars. So we can add them up and say, what's the input into the ISM from our known sources? And we'll even throw in supernova. There aren't that many supernovae. And then they wanted to know, well, did we make enough for the present day ISM? And the answer was no prior to this by a huge factor, like AGB stars could do 5% of the total, which was kind of sad. Everyone was sad. So they really wanted to know, okay, Karl, you've gone, before the measurements were based on Spitzer data or global fits to the global SED of the Magellan Clouds. What'd you get for your dust mass? I was like, well, I don't really care. Now you're going to make me worry about it. And one of the things I realized is, well, I better make sure that I get the right dust mass in the one place I have independent measurements of what the dust mass should be. And this is actually by looking at the diffuse, at the high latitude sky in the Milky Way. You correlate your measurements in different bands. This is actually from Kobe and Firas, Kobe and Derby. You correlate that with the H1 you see, so now you get a measurement of the surface brightness per column of H1. If I fit that with my model, I will then get dust mass per H1 mass. That's a gas to dust ratio. Oh, but I better get the right one. So you can actually, this is where the independent measurement comes in. If you use depletions, you measure what's in the gas phase for carbon and oxygen and iron, etc., which has been done in the Milky Way. There's a great paper by Jenkins, I can then say, ah, well, if I know how much carbon is gone because I assume, say, the solar abundances are the right abundances, I can just add up all those metals, the mass of those metals. It's always ratio to H1. I can now, I have a measurement of what the gas-to-dust ratio is in the diffuse size cell. And it's 150 for this particular set of data. Okay, so I better get, my model better produce 150 when I get done. When I fit my model, all the models better get it. And so then that's actually how I calibrated what the emissivity at 160 microns was from my model, right? So I know in one place where I do know what the dust mass should be, I'm getting the right answer. So now when all I'm saying is that the dust in the Magellan Clouds should be similar to the Milky Way. That's the only one we can do, because Milky Way is where we know most about dust. It might be wrong, and we're working on, there's a Hubble program that Julia's leading that we're working on trying to get depletions in the Magellan Clouds to test that statement. But that data is not here. So we went ahead and did that. We've calibrated it. Just a brief comment to say that the nice thing, and if you look at the green, is if I assume the data the bands are uncorrelated to the blue, where I put in my full covariance, you can see that one of the nice things about, in this case, using a better noise model, my uncertainties on my fit parameters went down because I've restricted the parameter space that's allowed by acknowledging the correlations in my data. So it's worth doing. You actually get smaller, you get more constrained data, more constrained results, which is nice. There's the maps. I don't think that's really too exciting to look at. More interestingly, I wanted to know which one of these models, right, was the best model. And so there's a couple of ways to ask that question. One is, what are the residuals? And so what I do want to do is just plot the residuals as a function of, say, surface brightness. And I'm hoping I don't see a trend with surface brightness. And I think maybe everyone might agree with me that of these three models, that one's the best one. And then the referee maybe put in chi-squared, average chi-squareds, although what a chi-squared means when you have correlated data is a little interesting, but maybe the relative is interesting. I don't believe the absolute magnitude. So okay, so this looks pretty good. The broken emissivity modified black body fits the data better than the 2 temperature modified black body. Okay? Not even when I don't have to appeal to anything else. It just describes the data better. Okay? And then there's the other one that really is, for me, the death knell of the idea that we could have some low, some less than 10 Kelvin dust that makes up for this submillimeter excess. And that's if I put in the gas-to-dust ratio that I get from the 2 temperature modified black body. I get a gas-to-dust ratio that's so low, it's below even what I could get from maximum depletion. I take all the metals and I put them into dust. Right? So that's this region and above. Reasonable depletions are if I scale what we see in the Milky Way by the metallicity of the Magellan Clouds. And we do see a range of gas-to-dust ratios in the Milky Way. That's what's the blue region. So these are the two models that actually, there's only 2 models that actually fit for that constraint. The 2 temperature modified black body really is out. And if you go back to there, the residuals really tell me that I need something to deal with this submillimeter excess. And it really looks like a broken emissivity law is the right answer. In hindsight, this is obvious because the laboratory data was coming out telling us a broken emissivity laws were what we should have been using. But still, you got to push through and do it because even until you do it, they're not going to accept it. So it gets hard at the end when you know the answer and you're just trying to get the paper out. It's worth doing it. I'll get citations, but mainly for, did I put it in? Dust masses. So I actually calculated the dust masses. Right, you add them all up. Now I didn't fit things that didn't have good measurements. So there's the dust masses for everything that was well detected in an individual pixel. And then I went ahead and did stacking analysis to do all the ones that were too faint. So that I had all the dust mass, and here are the dust masses you end up with. And these are 4 to 5 times lower than the previous estimates. So all the AGB, all my friends who do AGB stars were very excited. Because now instead of 5%, they're more like 20 or 30 or 40%. They can account for a bigger chunk of the dust mass in the present day ISM. They're back in the game. They'll even go so far as to say, well, maybe we can do it all. We just have a factor of 2 to 5. So that's all right. I should go back and say there are lots of correlations. Things as simple as, I can use the pointer maybe.
Sorry, can you bring up a couple slides? You had one where you were comparing the measurements to the maximal depletion and reasonable depletion. with SMC and LMC, right?
Yes.
I mean, if I ignore the error bars, the SMC sort of, it's not really in the reasonable depletion range. Is that what you're seeing?
Well, no, so reasonable, right.
It's reasonable.
Reasonable means scaled from Milky Way.
Scale from Milky Way, right.
Right, so
Okay.
you're correct. The SMC, it's our 1/5,
That's
has
where
a,
we're going from the phase transition from.
yeah. So there's something, it's not like the Milky Way scaled down. There is something else going on there. You know, okay, the error bars are close enough, I'm not gonna make that, but there are other indications that the SMC is in a different place. Right, we see this in the XO factor,
Yeah.
or if I was to get away from the XCO, we see this by the fact that as you go down past some metallicity, it's very difficult to detect CO, period.
Or pause.
Pause are also dropping in a similar place, yes.
Which would imply the molecules in general.
But we do, that there are places which have strong POM emission in the SMC.
Sure, but it's got to be the density and pressure.
It may be as simple as the covering factor, right? There's just so few molecular clouds, right? They might have all normal Milky Way type emission, but there's just so much fewer than when you look at the global thing, you're completely dominant. Just change the ratio of how much emits pause and how much doesn't emit pause. And you might be able to see, you might be able to get the metallicity trends.
So why did the dust masses go down so much? Is it just by changing the emissivity?
The dust masses went down so much partially because we were able to do a resolved analysis. And if you look at this one here, you can see that we have a large range in temperatures, right? Large range in masses. And if you were to add all that up together, right, it doesn't add linearly because you're adding the emission from these black bodies, not right the mass itself, which would add linearly. And so we went from taking the global thing,
Which is luminosity weighting.
which is luminosity weighting, to where we can, we think in 10 parsecs, we're starting to get where our assumptions are not that bad, right? And so that's one reason. And I'll tell you that, and Carolyn Bott was one of the ones that gave out the masses before. She did it from the global SED that had been measured with lots of instruments at all wavelengths. But she's like, I didn't really care what the total was. That wasn't what her interest was. So you put it in and you did standard assumptions, but you didn't worry about making sure that you got the right dust mass, say, for the diffuse ISM in the Milky Way. So one of it is we calibrated things. One of it is we had better data, right? So we paid attention. There's also, I don't have the slide somewhere buried in the vaccines. It also really matters whether you take into account the correlations. And it also matters on how you actually add together all the pixels. So we didn't just add the best fitting value for each pixel or the 50th percentile. We actually did realizations for each pixel and then added those together and did that again and did that again to try to, because the likelihood functions that are coming out of the fits are not Gaussian. And so you need to take that into account, the non-Gaussianity, in order to get a good total mass. And so so there's a number of things, and these can be factors of 2 easily. So how you treat your data, how you treat your results really can impact things when you're adding things up. That are not going to be, that if you don't have Gaussian noise, life is not so simple.
So at least for the temperature variations, does that mean that for any galaxy beyond redshift 0 something, we can never get a reasonable dust mass estimate unless we assume some distribution for temperature
Yes.
variations?
So I think we need to train ourselves on the local galaxies. And we should at least start, let's assume that the local galaxies that we see similar temperature things, and if that can reproduce the higher redshifts, then we're done, right? You can't get more complex than, right? So find out if you just translate the dust and the temperature distributions we see in local galaxies to higher redshifts, if that works. I mean, and they're not all going to be the same, right? The SMC is not going to be the same as the LMC. So there is going to be some variation in there. So that would be what I would advocate. I might have advocated that this morning in someone's office too. More talking, and not just talking, but actually working together. I think that's the thing I haven't seen is the local universe people working directly with people and looking at galaxy evolution. But that's okay, that's another topic. I think I'm going to skip over these just to get to the beast because I really want to explain the acronym because I'm just so happy with it. So now, more recent stuff, which I got involved in because of the FAT survey, which is let's use star counts. This is me, you always go back in time. So, star counts is another way of mapping dust. You map dust by counting background stars. So in the Milky Way, you've seen all these pictures of the Bok globule. You see all the stars around it, and they go down to nothing inside, right? So you could quantify that by measuring the density of the surface density of stars outside. Measure it as you go in, and that will tell you what the AV distribution is as you go into that Bok globule. That's star counts. Straightforward. Lower density stars, higher AV. Stellar populations don't change over the area on average, and that probably works over a small region of the Milky Way. Probably the latest stuff is the nicest code, which tries to deal with foreground stuff and all that. That's great. In nearby galaxies, that's going to be a little harder, right? We don't really see those nice Bok globules usually get isolated put out. So now we have to actually model the stellar populations at the same time as dust. And we need measurements to individual stars for this to work. We're trying to just take star counts and move it into nearby galaxies. And so this really, for me, started off with these Hubble observations of M31 from FAT. But now there's observations in a lot of other local group galaxies similar to this. And so, I'm just going to keep going. So FAT. FAT is this, and for me it was a little revolutionary, right? The idea that what we're going to do now is we're going to get a big chunk of a local galaxy, and this is 1/3 of M31, and we're going to measure it in the near UV out to the near infrared. So we're going to resolve stars over that broad wavelength range. And then we're going to kind of see what we can do, right? We knew we wanted to do things. I didn't think we could do as much as we're actually doing. It's a big program. Those are the bands. There's over 100 million stars, right? They've done photometry, complicated, individual band, all the bands simultaneously, forced PSF fitting photometry, the best stuff you can do. Lots and lots of data. This also was my introduction to big data. Now what are you going to do? I'm used to working on small samples. This is not a small sample.
How many astronomers did that support?
A lot. But there's a lot of papers out of it too. This is really, for me, this has started a new direction for me personally, and I think some other people, that this is the kind of data. If we get this kind of data, not often in the past, stellar pops, resolved stellar pops work is done. It's been two bands, often like R and I, right, very near in wavelength space. And there's a lot of work, great work that's been done out of that. But it turns out if you get a broad wavelength range, right. Now, this is the slide I skipped over. Now you can do something, right? This is an old standing stellar temperature versus dust reddening. Either you can redden your star by putting more dust in front of it, or you can just make it cooler. So somehow you have to break that degeneracy. And if you have a long enough wavelength baseline, you can. The shape variations from dust are different than the shape variations from the stellar physics. Okay? So that's all this is based on. This is not very complex, although given its big data, I guess we had to claim some complexity. So here's the beast, Bayesian extinction and stellar tool. Brilliant, there's no extra ones. I'm not using anything at the end of the word. Come on. All right, so this is an SED fitter for individual stars. It does both stellar and dust. It uses Bayesian techniques. An accurate noise model for crowded data, and had to be fast. And so this is one of the things, there are other SED fitters out there that do a great job, but I'm not going to throw 100 million stars at them. And so that was one of the things we had to do. It takes like 13 seconds per star. But now think about that to 100 million, how much CPU hours you need. It's not a small number. It's now open source. We just put it up. We made it open source a month or so ago. So if you're interested, you're welcome to contribute. Keep trying. We'll see. So what do we do? What do I mean by a model of a single star in a galaxy? There's 7 parameters that tell you what a star's SED looks like. And we're using as much physics as we can get away with. Stellar evolutionary tracks give you the birth age, mass, and metallicity. Right? So that tells you how bright it is, its effective temperature, its log G. Then you use stellar atmospheres, Caru's, T lusty. That gives the translation between the luminosity and the actual detailed spectral shape as a functional wavelength. All right. Dust extinction curves, we then say, all right, AV, that's how much that is there. RV, that tells you some of the shape variations. But that doesn't tell you all the shape variations, and so we actually came up with a mixture model where we mix this RV-dependent law in the Milky Way with what we see in the SMC bar, which is no bump and very steeply rising. And it turns out that works really well to explain pretty much all the extinction curves we have in the local group. So the nice thing about this is 3 parameters, and it describes the detailed shape variations of dust. Okay? And the distance, which for M31 is effectively a delta function. For other ones, we're going to have to actually solve for it. The strengths of this is it's got this parameterized dust extinction model, and this is why I got involved in this SED fitting. It was mainly, I had thought I was going to use FAT as a target list to do spectroscopic UVs, to do UV spectroscopy of stars, of red stars, so I could do dust extinction curves. I didn't think I could do it with just the photometry. It turns out you can do pretty well. And I got involved because I knew that if I let the regular people who did it, they would assume RV of 3.1 was 3.1 and not change it and just go. And I wanted a little more information. Turned out to be pretty good. This is a collaboration. The BEAST is a collaboration of people who are very interested in the stellar side of it and the dust side. And we try to keep each other honest and don't let the other one make the assumption that is kind of sad. We also have the noise model, includes the covariance, of course, as well as biasing and so on. We do the Bayesian stuff so we can actually put in priors. This is how you construct it. There's your star, multiply it by the dust, and then you integrate over your band passes. Sometimes people do this, then that, and then this. That's not going to work well. Especially as the shape of your spectrum in the filter changes, it changes the effective wavelength of the dust extinction, for example. So you really want to do it in this direction. And I won't even get into filter red leads, which make it even more important. Here's just showing what this new mixture model is. This is the Milky Way RV dependence, so that's just the standard CCM or Fitzpatrick 99 as you change RV. This is if you fix RV and you change this mixture ratio, so you go 1 means your Milky Way type, which is, I think, where is it? 1 is, there we go, this one here, right? And I put the average Milky Way extinction on there to show it. And then the SMC is the circles and the green line, right? And so this is actually a 2 parameter, I'm just showing cuts through it. And so this, now I have ways to vary the bump strength and the far UV and everything together as we see them empirically. So that's the model. There's the fitting details. That equation should look fairly familiar. The one thing that might be interesting to point out is in our delta, there's actually a bias term. So when you're actually extracting photometry from a crowded field, you may not, even when you put in your artificial star, you may never get the input flux back out. It may always be shifted, right? Not just has noise on it. And that's a bias. Okay, that's nothing wrong with that. You have a nearby source, it always biases you positive. You need to put that in your model. One of the things to think about that really, for me, thinking about Bayesian and stuff taught me was, I'm modeling how my data is a combination of physics and the telescope and the instrument. And all I really know is the combination. So that means my model of the data better include what the actual observations do to my physics model. Right? That's the same thing again, we can calculate things easily. It's just a little look at prior, so I resisted for as long as I could, but finally gave in because they were right. For example, what kind of prior should we assume on the stellar populations in M31? You could argue for various things, but a reasonable prior is a scale of IMF, right? I know that more massive stars are going to be rarer, and a constant star formation. And this is what that prior looks like in 2 different ways of looking at the HR diagram. Right? There's an HR diagram. We're not going to see as many of these or these as we are these. Right? That's just the IMF plus the star formation stream.
Of course, if you multiply that by, convert it to a flux, it will shift, will change the distribution. Right, that's what you're really looking at here, not necessarily luminosity, which you're measuring on flux. And so you would want to weight this by the distance squared or something, right? That distribution.
No, I'm doing, no, so that's a good point. We are actually fitting in the luminosity space. We're not fitting like we're not normalizing the data by some average and then fitting just the shape. We're actually fitting the luminosity because we know the distance. And that is actually one of the keys of breaking some of the degeneracies. We know the distance. And so we don't just have shape to play with, we have absolute as well.
I guess even like the M31, the delta difference is not
It's like 1 or 2%.
Okay.
But we're going to do the SMC too, and I don't know if you guys have been following it. The SMC has a depth of like 30 kiloparsecs. It's insanely along the line of sight.
That's not good.
That's not good. So yeah, we'll. Is it really that bad? Yeah, it really is. Cepheids and Arliars, yeah, it really is that bad. I mean, it's like a cigar shape along the line of sight. Like maximally the worst case you could find. Yeah. All right, I'm running out of time, but let's see. So there's, you fit it, you get your likelihood functions, all that good stuff. So here's kind of, one of the nice things you can start to do is you just make the average AV in each pixel. This is a preliminary result from early fits. There's your AV distribution in a couple of bricks, and there's missing data. This was done before we had the full stuff on. That looks great, but now I can also make an RV. And you can see there are some spots that are a little higher in RV. It could be noise. Of course, I would be standing here if it wasn't that much fun. So here's the IR-derived dust surface density from Bruce Drain's fits. Okay. I can rate, these are both measuring the amount of dust. Right? They're both nominally, should be linearly related to the mass of dust. Yet, if I take the ratio of the two, there are places where clearly something's varying. The AV should be a more direct measure of the dust. The mass of this IR1, remember, we've assumed constant emissivity as a function of dust surface density, right? It doesn't matter where it is, but in fact, from Milky Way observations of star counts, surprisingly, maybe not, but we know that the emissivity as you go into a molecular cloud gets higher, right? Dust in molecular clouds is more efficient at emitting. And if I then put up the RV map again and make little circles to guide your eye, of course, you can actually see that where this is happening is in what we think is the molecular clouds. And by the way, we also have CO observations, and they also trace the same RV structures. And so we have a pretty good indication. We can now look at this and say, we can now start to solve for how the emissivity varies with RV.
What is the RV variation there?
It's not very big. It's maybe 3-ish here, and this might go up to 3.5.
Okay.
So yeah, on average, it does change, but it doesn't change huge amounts. I should say that there's just to show that you can do it even nicer. Julianne worked on a focus dust mapping using just RGB stars. You know where the RGB stars are supposed to be. It's a well-defined stellar population. You use the RGB stars in front of the disk. So if you think about it, in a galaxy, there's a dust disk, and for older populations, either half the stars are behind the dust disk or half are in front, on average. And so then you know the ones in front are unreddened and the ones behind are reddened. So you can use the distribution of these in front to calibrate what the color should be, and then you find out how much reddening you have to do in order to see what's the ones to match the ones in back. And you deal with completeness, you do with all the good stuff. And you can make a very nice near-infrared based extinction map. And you compare it to the IR one, and you can see, wow, we can at least do higher spatial resolution. It's always a positive. But also it turned out that these are both on the same scale. That's AV, right? You can scale the mass of the dust by the dust model used to AV. And if you look carefully, the scales are quite different. So in fact, the IR-derived AV is a factor of 2 or more higher than one we derived, that Julianne derived with the fat data. There was, at the same time this was coming out, there's also results from Planck that also say the same thing, that Bruce Drain's model is actually giving masses a factor of 2 or so.
Some kind of bias in the sense that you only ever see the brighter stars from the HST work.
No, we go way down.
Way down, so it's not the issue.
This is the difference, yeah. HST is, with this resolved stellar pops, can go to high AVs and low in the, depending on where you are in crowding, but you can get down to the solar mass. It's pretty, yeah, the data's pretty nice.
Okay, so essentially you're just missing a whole bunch of stars.
Yeah.
Okay.
Yeah. And I'll just briefly say we are trying to take this kind of mapping, but so we can also use the output of the beast and get RV maps and FA maps. With completeness, that's going to be called the Mega Beast. Once you have a good acronym, you just got to use it. We're working on this. It's a hierarchical model. The nice thing is we can just work on the outputs of the beast, and it's just like we're working with the fluxes. Right? That's the nice thing about such kinds of hierarchical modeling. Basically, the reason you need to do it, here's if you just do the average AV. You just average the AV in your bands, and you can imagine completeness. It's going to give you very interesting biases, because as you go to high AV, you're not going to see those stars, and so you're always going to be biased low. But if you don't have much dust in that pixel, you're going to see the whole thing. You're going to be very complete. And this is just a very preliminary. Don't get too excited. We're still working on it. But now our AV maps from the beast match pretty well with the contours, which are the far infrared. And we need to refine it and do a significant amount more work before it's quantitative and ready to go. But we're working on that. And then I want to stop there. I'm just stopping the outline. There you go.
So the regions and the stuff that you've been modeling is fairly, I mean, just normal. It's not like crazy regions of star formation or anything like that. So could you completely, off the record say how you think you would be able to adapt your approach to perhaps try to model the more extreme conditions?
So do you consider 30 Doradus extreme?
Yeah, ish.
Ish.
Yeah.
So we will do the beast kind of analysis. There is the HTTP survey, which is a region like 20 arc minutes with similar kind of data to FAB around the whole Hubble, the whole tarantula region, the whole 30-hour region. So we'll do that. So the problem with this, with the beast kind of analysis, it's going to be hard because we need to resolve the stars. And so we can probably push out a few megaparsecs. And so I don't know, it depends on what galaxies.
Right, that's the problem. If it's in this local volume, you're not going to get really crazy,
That's correct.
extreme conditions.
Right. So we can do the IR analysis in more distant things. You just start to have bigger and bigger physical regions, and so you're mixing more and more. So it's not clear how, I think that's one thing, but that's one thing we should be able to test, right? Especially on the local ones. How well can we, we can always make them lower resolution.
What's the metallicity of 30 Doradus, that region?
It's one half.
One now.
Yeah, most dwarf galaxies seem quite well mixed in metallicity, and the Magellan Clouds are well mixed empirically measured, right? Both from stars and gas lines. Ivan?
Can you show that RV map? So what is the range of RV you're getting here?
As I said, it's maybe about 3 here, maybe 3.5 at the peaks.
Also, it's still from, it's a small range.
Yeah.
So this is still not the kind of RV we are finding from supernovae,
No.
which goes from like below 2.
Yes.
Yeah. So most of our RV in this highly extinguished dust
Yeah.
environment is below 2.
In the highly extinguished, interestingly enough, that would be molecular regions, and the RV should be higher. Because the RV, usually we think of RV as tracing the average grain size. And in molecular clouds, the average grain size is going up, right? There's coagulation.
So what we're saying, actually, even in those cases, we are probably not going through molecular clouds. It's even more like through a very diffuse area, but
Yep.
something like maybe aligned with the disk or something.
So I think in particular for that, the supernova stuff showing low RVs on average is surprising from looking at M31, where we're seeing RVs of 3 right there. The average is kind of where you'd expect it to be. We're seeing that in, that's been, Eddie Shafley's seen that in the Milky Way, he's maybe 3.3 instead of 3.1 is the average, et cetera. So it's surprising that supernova all have lower. The one thing that I asked this earlier, if they really are probing circumstellar matter around these supernova, the thing that I don't know the answer to, and I would love to know, have there been any, you've got circumstellar matter, you're going to have scattering back into the beam. You're going to have to do some rate of transfer calculation to account for that, right? So the RV you're measuring, if you assume, you're just trying fitting it like a screen, right? The RV is probably not the real RV. It's not actually diagnostic of the dust grains directly. And I don't know if anyone's done that.
Yeah.
What if you put a little bit of dust in a shell around it doesn't matter if it's a supernova, whatever. How does that change the derived, what I might call now an attenuation curve, which includes the effects of radio transfer?
Yeah, that's been calculated, but even after accounting for that, we still have this real interstellar for the extinction to show RV that is very, very low. It's very strong extinction.
Okay?
It's not.
Saying the extinction
It's
is
not
high.
circumstellar. This is that I'm talking about. That's separate. So there are real strong evidence for interstellar clouds, interstellar medium dust, to produce very low RV.
But you're saying you don't see that.
But we're not seeing, so where we
You're not
measured
seeing
it with
here,
a
so
different,
that's curious.
where we measure it with a different technique, we're not seeing that.
Yeah.
And so one of the differences are, I would argue that we understand the physics of stars better than we understand the physics of supernovae. And so there's always a question in my mind, is there something about the analysis where what you are assuming for the unreddened, the unextinguished supernova spectrum?
That's, I think, we are fairly robust on that, because we also got very broad wavelength coverage, and this thing is done by.
I understand it, but you see there's this tension, right? We're not finding it with other techniques. We're not finding these low
Right.
RVs
Yeah,
systematically, right? And if supernova are an older population that goes off, they should just be sampling a disk. There shouldn't be a preferential treatment.
Someone tried
But
to
you
not
must
do
get
it. Sorry, with like supernovae, I mean, there's prime reflections all the time. Can you count the supernovas recently seen? The reflection of the supernovae off, the back and that's some.
Maybe we should take this off.
Yeah, okay, I'm just curious.
So you must get some millions of kind of independent data points from the other values. So what is
Yep.
the distribution?
Oh, I hate that thought. I mean, when we make the maps, the RV is on average around it, but yeah, we should make the distribution here quite good.
I mean, there must be some, we can point to a few objects in the Milky Way where RV is 1 and a few that are 7 or 8 or something.
No. Milky Way goes 2 to 6, that's all you get.
I
2
know
is
one
the
example where it's not that. But okay.
Well, okay, I'd like to hear about that. But to my knowledge, we go 2 to 6.
So,
And I would love to have that reference.
So another question that I have is about this covariance between AV and RV in your analysis. This is basically you're gonna use that extinction curve somehow weighted by your data. So
I don't have a plot of it. We have done sensitivity tests where we input and see how well we can recover RV and AV, and we can recover both of them quite well if we have a broad enough wavelength. Because again, adding more dust, making AV larger, it has a different shape variation than changing RV.
yeah, so that creates some covariance.
There will be, yes, oh yeah, everything comes out of this is going to be correlated at some level.
Yeah.
And now we'll have to acknowledge it because we can. But I don't have the visualization like I did. We haven't done the realization, because you also need to, when you're making those correlation plots, they look much different if you use, say, the maximum likelihood as versus actually having, say, a realization. What I'm trying to do is make a plot that actually encompasses the uncertainty as well. If I only had 10 points, I just put error bars on. You can't do that when you have a million. And so you take one sample out of each likelihood function for each star, and then you make the 2dP out of that. And that will acknowledge the uncertainty.
So
You can make 4 or 10 of those, look at them as a movie and see if they vary.
Yeah, it's kind of complicated, but if you do a bootstrap on the color or something, you should be able to back that out.
Well, I can calculate it. So this kind of Monte Carlo stuff is the frequentist side of the probabilistic side of Bayesian. They should get equivalent results.
If you believe your errors.
You must understand your errors. So the B stuff is nice. We are empirically measuring the errors by inserting stars one by one into the data and re-extracting them with exactly the same algorithm. So we should empirically be capturing everything except the absolute flux covariance, which is captured by the actual stars used to calibrate Hubble. So I can at least argue we're doing it.
Any questions? Well, we have used your time. Let's thank Karl again.
Take the lunch. If we didn't have scheduling grad harassment.